In this video, we are going to find one of the very important technique of finding numerical solutions. What are the numerical solutions? Or we sometimes also call approximate solutions. So why we need approximate solutions? Like most of the equations that we encounter in our studies are hard to solve. But here we mean by solve means we try to find the exact solution. So it's really hard to find the exact solution. So for example, let's look at this problem. So let's say we have Ex equal 2 cosine x. And these kind of equations are like what we normally call nonlinear equations. Linear equations are very easy to solve, but these are nonlinear equations. So you don't get lines here. So if you look at the graph, this is the graph of this function. So if you bring it to one side and if you try to graph it, this is what happens. So, and then you can see that uh, there are some solutions. Like for example, at this point there is a solution, so we can call this solution x star. So there is a solution, and there are like in this case actually there are infinitely many solutions, and you can see that there are solutions everywhere. There's one here and there's also another one there, another one there. So there are infinite number of solutions for this one, and there's a one positive solution. So the question is how we can find it. Is there a way to find the exact value? And you can show that there is no way to find the exact values for this particular problem. For example, if you plug in 0, you can see it doesn't match. If you plug in 1, it doesn't match. So that means for this particular situation, you cannot solve exactly. So instead, what we're going to do, we're going to find what they call, so like it's really impossible to find the exact solution. So instead, what we're going to do, we're going to find the approximations. So we're going to find approximate solutions. So how we do it? So that's the question, like how are we going to find the approximate solutions? So that's the goal of this video, like what we're going to do with that. So for example, what we can do is just like a simple idea. Let's start with a point close to the 0. So you're going to find a point like somewhere here. That's I'm going to call the initial guess. So some value, let's say 1. Now what we're going to do, we look at the tangent line at that point. So we go to the graph and look at the tangent line. So if you look at the tangent line, and you can see that if you draw the tangent line, this is what you get. So this is the tangent line. So now what we're going to do, we're going to look at the new value over there. So we get the value where the tangent line cross the x-axis, and then look at this one, and then do look at the tangent line again. So the new tangent line is this one. And then you can see that every time it's getting closer and closer to the actual solution. So you can see it's getting closer and closer to the solution. So this is the idea. So this is the solution, and you can see every time when you draw the new tangent line, you can see it's getting closer and closer to the 0. So that's the idea of the Newton's method. So let's try to derive the formula now. So let's look at this graph. So what we're going to do, as before, we're going to start with the point somewhere here. So the goal is to find this 0. So we're going to call x star. So we're going to find that. What we do, we're going to start with some point nearby. But this is just exaggeration, just to tell you what's going on. So let's pick a point. That's what we normally call x naught, the initial guess, because this is the initial guess. Now what we can do, we draw the tangent line. So let's draw the tangent line. So this is the tangent line at x naught. So you can see it's going to cross the x-axis at x1. Now what we can do, we can look at this new value, and we're going to find the tangent line at this new point. So let's draw the tangent line at that new point. So you get this. So you get this one, and then again we're going to find the new point, which is x2, and then we're going to find the new tangent line at that point. So you just keep doing it until you get close enough to the 0. So that's the idea. So that means what we simply really need to do here is we need to find the equation of the tangent line at x0, and then we're going to repeat it. So let's try to do that. So how we can do it? So so this is like a, so we can see if let's call this function y equal fx. So we're going to call this function y equal fx. So that means this point here is x naught f x naught, that's the point. So what we're going to do, we're going to find the first tangent line. So we're going to find this tangent line. We're going to find the equation of this one. So how we do it? We know the slope is the derivative evaluated at x naught. So that's a slope. So slope m equal f prime x naught. We assume that this is not equal to 0. And then let's try to find the equation of the tangent line. So the equation of the tangent line, equation of the tangent is simply y minus f x naught, that's the y value, equal f prime x naught times x minus x naught. So that is the equation of the tangent line. So now what we need to do is we need to know when this meets the x-axis. So when this meets the x-axis, so that means when y equals 0, so when y equals 0, that's when this meets the x-axis. So we're going to set this equal to 0. So that means it's 0 minus f x naught equal f prime x naught, and this x value become x1 now. That's when this tangent means the x-axis at x1 minus x naught. So now what we need to do is we're going to solve for x1. This is very easy to do because we assume that f prime x naught is not equal to 0. So we're going to divide by that. So we can write this one as negative f x naught over f prime x naught, so which is equal to x1 minus x naught, and then we can solve for x1. So if you move x naught to the other side, you can see that you're going to get x1 equal x naught minus f x naught divided by f prime x naught. So this is the formula. So this is the formula where you can find x1. So the goal is to, so you start with x naught and then we use this formula to find x1. And then once you find x1, now we use the same formula again and plug in x naught. Wherever you have x naught, now you plug in x1. So then once you plug in x1, then you get x2. And then wherever you see have x naught, now you plug in x2. So then you get x3. So we just keep doing it until these numbers are getting close enough. Or what we normally call the value is going to converge. So this value is going to converge to the 0 that we are looking for. So that is the idea. So we're going to keep doing. If we start with x naught, that's the initial guess. That's a guessing value. So this we don't know. That's why we call x naught. We don't call it x1 because it's just a guess. So x naught, we only call initial guess. And then we're going to plug in the x naught to the equation and find x1. And then you get x1 and you plug in back into the equation, get x2. So you keep doing it until you get until you see these numbers going to converge. So it will be very clear when you look at the problem. So let's try to write all those formulas now. So so the solutions of x naught equals 0. So that's what we're trying to solve. X naught, solutions of fx equals 0 are approximated by, it's never give the exact values, approximated by this equation. This is like what we normally call algorithm. So this is the algorithm for that. So it is, so if you know the xn value, it's going to give you the next value. So that's the idea. So if you know one value, it's going to give you the next one. That's why we write it at xn and xn plus 1. And we only assumption is we can assume that the derivative of evaluated at the first point or the initial point not equal to 0, and then the coming ones, like for example f prime x1 cannot be 0 when you want to find x2. So it's just like that. And this formula is true for n going from 0, 1, 2, 3 like that. And then with the initial guess x naught, that's x naught. So x naught is the initial guess. So when you plug in n equals 0, you get the first value. And then when you plug n equal 1, you get the second value, just like that. Okay, so so let's try to look at let's try to solve the problem that we could not do and see, like, how successful we are. So let's look at the problem. So find one positive find one positive and one negative solutions of, we know that there are infinite many solutions, so let's try to find one positive and one negative. So let's start with one of the initial guess. Let's start with x equal 1. So that may be a good guess. So what we can do, the starting, so this is how we like kind of do a problem like this. So what we do, we can write this one as an equation, and then you set that equal to 0, because you try to find zeros. So we can write this one as first, so we have ex minus 2 cosine x equals 0. That's the first step. And then we're going to pick this part as the function. So we're going to say let fx equal ex minus 2 cosine x. So that is the function we are talking about. And then what we need? We need the derivative. So we're going to find the derivative of this one. So which is ex minus, a derivative of cosine is a negative sign, that means become plus 2 sine x. So it can be any function. It can be any function. So we have this one. So we have the two function and the derivative. Now we're going to plug into the formula. So let's try the formula. So the Newton's formula becomes, so the Newton's method, what we normally call Newton's method, becomes x n plus 1 equal xn minus, so let's plug in. So what do you want to plug in? You want to plug in the xn to the function first, so which is e to the xn minus 2 cosine xn. That's the first one. The second one, the bottom one, exn plus 2 sine xn. So now what we can do, so that's the formula. This is true for n going from 0, 1, 2, like that. And then we're going to start with the initial guess. So let's say our initial guess is x not equal 1. So what we do, we're going to plug in 1 everywhere you see xn. So you're going to plug in here, you're going to plug in there. Everywhere you see xn, you're going to plug in 1. That's what you do. So let's do that. If you do that, this is what you get. So we have the equation for n equals 0. This is what we have for n equals 0. So we're going to plug in. So the guess, so we say initial guess. Let's say x not equal 1. That's something you select. Sometimes it's going to fail. So let's plug in that. So if you plug in that, this is what happened. So make sure that when you use a calculator, the calculation is in radian mode, because these are not degrees. This has to be radian. So that whenever you use calculus, make sure that you are in the radian mode. So if you use a calculator and if you approximate, you're going to get let's say up to 4 decimal places, 0.6279. So see whether you get the same answer. So we don't write too many digits right now, because like it's like a initial value. Later we can add more digits. When the things are getting closer and closer, we can add more and more digits. Okay, so this is the first approximation. You get x1 as 0.6279. Now what we can do, we're going to use this new value and we're going to plug in this new value to get the second value. So for n equal 1, so when you say n equal 1, what happened? This side become x2 because n plus 1, and then you have 1 everywhere. You have x1, all the x0 now become x1. All of them become x1 when n equal 1. So that means you can plug in these values to the equation. So it's going to get 0.6279 minus e 0.6279 like this. Again, if you use a calculator, so it's approximately you're going to get 0.5442, and you can see there's number change. Now we just keep doing. So and then when you plug in 0.5442, you're going to get this. So I'm going to write the first few values now. So we start with x1, actually x0. We start with x0, which is equals to 1, and then we have x1. We approximately we get that one as 0.6279, and then we use this value, and then we're gonna get x2 as 0.5442, and then we use this value again, so we get x3 approximate. This is all approximately equal. So we have to say approximately equal. So you're going to get 0.5397, and then now you start actually seeing some numbers fixed. You can see the first digit is fixed now. So let's plug in that one back into the equation. So when you do that, you get as x4. If you look at the x4, and you can see that it's 0.5397. They're all equal now, and you get. I'm going to add a few more now, because since those numbers are, whenever you see numbers are fixed, try to add few more. So when you add that, then you can see your x5 becomes, if you plug in the value again back into the equation, and you can see you're going to get 0.53978516, and you can see that they are exactly the same. So what does that mean? This number doesn't change. So that means this is correct up to how many? There are 8 digits. So there is correct up to 8 decimal places. So you can say this is correct up to, so correct up to 8 decimal places. So you can see that just calculating 4 times, you can see you calculate 4 times. They start with the first one, that's the first calculation, the second calculation, third calculation, fourth calculation. So if you do just 4 calculations, you can see you get the answer correct up to 8 decimal places. So you can see this method is really accurate, really good. So that's the idea. So that means you can say the solution. So you can say the positive solution is the positive solution is approximately 0.53978516. So that's the idea. So you get the value. So what we did, we look at the equation. We first start with the function, find the derivative, plug into the equation, and then sometimes we simplify it. So we see in the next example, we're going to simplify. We don't use it like that, because just to make the algebra easy. And then just repeatedly plug in. You start with first value and then repeatedly plug in until you see those values going to converge. Like they're going to be the same. That's converge means. So you're going to get closer and closer to each other. So when that happen, you get the solution. So you just need to like multiple calculations, and that's it. So let's try to see how to find the negative value. So we do the same thing, but we start with the negative value. Now to find the negative solution, what we can do, we can start with the negative value. So let's say like for example, because we don't know anything, we just start with the value. So let's say x0 equal -1. So you can pick any value, like don't pick like a value like too big or too small. So let's say x0 is -1. So we can plug in the value to the equation. So for so x1 as before, you can calculate x1. So we're going to plug in this value. So it is, so when you use a calculator, and you're going to see that you're going to end up getting -1.5. We are not going to write more digits right now, especially at the beginning. So you get so you start with -1 and you end up getting -1.5. Now what we can do, we're going to plug in that value back into the equation. So x2. So and then once you do the same calculation, so you can see you get -1.4539, and you can see that it changed. So start with -1 and -1.5. Now it is -1.47. So you can see the first digit is fixed now. So no change. It even happened the last time. So now we can plug in this value back into the equation. So you get x3. That's the third approximation. Let's say x3, third approximation, which is negative. You're going to get see that -1.45339 3, and then 6, 7, 3, 6. So you can see that these three have already 4 digits are the same. Now we plug in that value back into the equation, so the new value back into the equation, and you get CX4. You can see that you're going to get negative 1.4536 and then 736. So you can see they are the same, and some other digits, and you can see that these two numbers are equal for up to 7 decimal places. So you can see this is correct up to 7 decimal places. And since these numbers are the same, we can stop here because you see that. So if you need to find correct up to 2 decimal places, and you can see that you can stop after x3. If you need more decimal places, you keep doing until you get more and more decimal places. So you can see that this is correct up to 7 decimal places. So this is correct up to 7 decimal places. So that means your negative solution is, you can say this one correct up to 7 decimal places. So you can say the negative solution is one of the negative solutions. There are infinitely many negative solutions, and then again just pick other values, like for example -2, and see whether it's going to convert. Sometimes when you pick a value, you don't see these values getting closer and closer. So it should get closer. If the value does not get closer and closer, what do you do? Because you pick a wrong guess, the initial guess is wrong, so you just find a new one and use a new one and see whether you get a new value with the new one. So that's what it is. Just keep doing it until you get values getting close. So it's always a good idea to look at the graph. The graph going to tell you like what are the kind of good initial guesses. Yeah, so that's kind of starting point. Okay, so let's look at a different example now. So this is how you kind of solve any problem. So you get an equation, bring all the terms to one side, and then use that as the fx function, take the derivative, plug into the equation, and start initial guess and start calculating values. So it's so simple. So let's try to look at a different example. How about this one? So the next problem is use the Newton's method to find the sixth root of 2. The sixth root of 2 correct to 8 decimal places. So you need this one correct to 8 decimal places. So the idea is the same. But how to start this problem? So you say you need to find the sixth root of 2. So that means you need to come up with the equation for that. So what we're going to do, so the answer, so what we're going to do here is, let's say if x equal, so we're going to say this one is x, whatever the value you have. And then you try to kind of get like a nice equation. So one thing that we can do is we can get the sixth power of both sides. If you get the sixth power of both sides, you can write this one as x to the 6 equal to, because if x is the sixth root, then if you raise to the sixth power, you get 2. Now what we can do, we're going to bring everything to one side, so we can write this one as x to the 6 minus 2 equals 0. So that's the equation we are talking about with the 0. So there's a 0 in there. So now we can define a function. So we're going to pick this part as the function. So we're going to say let fx equal x to the 6th minus 2, the starting point, and then we can find the derivative. So if prime x equal 6th x to the 5th, if it is a derivative. So now the Newton's method you can write. So the Newton's method, so it simply become x n plus 1 equal xn minus fxn divided by f prime xn. That's a formula. So let's plug in it here. So if you plug in, you get xn minus x to the n 6th minus 2. That's the top. The bottom is a derivative, which is 6x to the n, xn to the 5th power. So that is the formula. There's nothing wrong with this one. But what we normally do is we're gonna simplify this one if you can, just to make the algebra easy. So we're gonna simplify. You don't have to, but if you simplify, it's gonna make it much easier. So we're gonna simplify. If you simplify, what will happen? Just take the common denominator. If you take the common denominator, you can see that you're gonna get 6x to the 6th. So we subtract 1. So that means it's gonna be 5. So that means you can write this one as 2 plus 5x n to the 6th power divided by 6x n to the 5th. So that is the formula, and then you can see that you don't have any more negative signs there. So it's comparatively easy. Now what we can do, we can use some initial guesses and try to find few values. Yeah, so let's do that now. So we're gonna create the following table. So for each n. So we can start with the initial guess n equals 0. Let's say x naught equal 1, the initial guess, and then we start plugging those values. So we're gonna get for 1, you're gonna get x1 approximately equals to 1.167, and then for 2, you can see that x2 approximately equals to 1.1265, and then for third one, x3 approximately equals to 1.122625, and if you plug in that value back into the equation, x4 simply becomes again 1.122625. It's very interesting, and you can see those two are the same. So that means just after 4 steps, and you can see that you get the solution there. So this is like very interesting argument. So this is where we're going to stop, because you can see, because those numbers are the same, so we're going to step. So it's correct up to 8 decimal places. So if you need more, you need to keep going. So so we can say since the last two entries agree to 8 decimal places, you can write it like that. So you can say since the last two entries agrees to 8 decimal places, you can say 2 to the 6th root is approximately equals to 1.1224625. So that's the idea. So it's like very simple. So you start with what we did at the beginning. We say x equal whatever we want, and then we bring it to the 6th power and write this as an equation. So that's the idea, and how to solve. So we can do the same thing to find square root, cube root, anything like that, or solve any equations like that. So it's like very simple idea. And these are the only two different type of problems you get, because everything else you can bring into one of those forms. So now try to do these problems as practice problems. Now try to do these 3 problems. The first one is asking, find the real solutions, because you cannot find the complex solution using this technique. Find the real solution of the following equation. So we have x3 equal x cube equal 2x plus 3 with the initial guess x naught equal 2, and you know there are 2 other solutions that may be complex, but we just try to find one. And then 2 to the x equal 2 minus x squared with 2 initial guesses, x naught equal 1 and x naught equal negative 1. Maybe some of them doesn't work. And then sin x equal x squared minus 2. I'm going to let you figure out what may be a good one. So the good idea would be graph it. Just try to bring all the terms to one side and graph, and then you can figure out what may be the good idea. Good initial guess. And the next one is use the Newton's method to find the 5th root of 3. So this problem is very similar to the second problem that we did. Correct to 8 decimal places. Again, to 8 decimal places. So you can see it's going to converge really fast. And the last one is derive the Newton's formula to find the square root of a. So let's say you are given a, and you to find the square root, and what is the formula should be. Actually, this is like a kind of formula that Babylonians used for so many years. So we can derive the same formula, and then use it to find the square root to correct to 5 decimal places. So see whether you can do this, and then you can see the solutions in another video. Thank you so much for watching.